Today we're going to talk about indirect proofs. Let's take a look at the following statement. If an angle is a right angle, then it is 90 degrees. Think back to chapter 1. If we're given this statement, what's another statement that we could write which would also be true? We can use, if an angle is not 90 degrees, then it is not a right angle. We can say this based on one of the basic principles at the beginning called contrapositive. Remember what contrapositive is. It's taking the if and the then statements and switching them, but also negating them. The contrapositive of any statement then, if the statement is true, the conditional is true, then the new statement will be true. Now, also with contrapositive, if the initial statement is false, so let's say we started with this statement, then the contrapositive, again, negating this, and then switching this, is also true. We're going to use this kind of theory and concept to help us to prove indirect proofs in this lesson. Let's look at example 4 on page 213. We're given angle H is not congruent to angle K, and we are trying to prove that segment JH is not congruent to segment JK. Now, this is quite different than what we've seen in the last couple of chapters because this is a negation and not just a simple congruency. Proving negations of things or not congruencies of things is a lot harder than trying to just prove the congruency of things. So let's think about this for a little bit. If we know that angle H is not congruent to angle K, there are only one of two possibilities. Those possibilities being that JH is congruent to JK or JH is not congruent to JK. Let's just say or pretend that it is going to be congruent. So we'll mark our diagram appropriately that JH would be congruent to JK. Well, if those two segments are congruent, then we would know that angle H is congruent to angle K based on a theorem. If we have congruent sides of a triangle, then the opposite angles will be congruent. So we know that if we have congruent sides, then HK and angle H is congruent to angle K. Well, think about what this means also then, about the contrapositive. The contrapositive takes the two statements, reverses them, and negates them. So what this is really then saying is that if angle H is not congruent to angle K, then line segment JH is not congruent to line segment JK. And again, this is based on the contrapositive. In these types of proof, we're going to do chain of reasoning instead of a typical two-column proof. I do want to see the supportive reasoning behind it, but it doesn't need to be as formal. Now, in this case, this is kind of like a two-step problem where we go right from the if to the then. With these, though, there might be more to it where we're going to have a chain of reasoning, where there might be multiple steps in here. Because of chain of reasoning, we can kind of cancel those out and kind of think of it as the transitive property to get from the if statement to the then statement, and then finally to the conclusion. Let's look at now example 12. We're given circle O, and we're given that HE is not perpendicular to a perpendicular bisector of line segment DF. What we're then trying to prove is that line segment DE is not congruent to line segment EF. Now, normally what happens is that we see the given as the if and the proof or the conclusion as the then. And that's where we find the segments and we negate it. And so now we need to kind of figure out which we're going to draw from. The trick is to find the negation. So right away, the proof part, that's easy to find. DE is not congruent to EF. So that's the one negation. The only negation, though, in the given right here is that line segment HE is not perpendicular bisector of DF. So again, if we think about that, there's only two really possibilities. Either DE is going to be congruent to EF, or DE will not be congruent to EF. But let's assume that it is. I'm going to assume that DE is congruent to FE. And what we're trying to find out now is HE going to be a perpendicular bisector of DF or not? So one way we could do that is to prove congruent triangles or using the equidistance formula. And you may see two larger triangles with inside the bigger orange triangle. But what we can also do though is we can draw to the center from D and F, and that creates more triangles in there, which will help us kind of figure out more congruencies or the equidistance. We can draw those again because of the reasoning 2 points determine a line. And from there, and the reason why we chose those is because those land on, or they should land right on the outskirts of the circle from the radii. And what we do know about that, or we should know about that, is that all radii are congruent. Therefore, DO will be congruent to FO, again, because of all radii being congruent. Now, if you look at this picture, you see the two sets of congruent segments going to the end point of the segment. Therefore, you can then say that HE is a perpendicular bisector of DF based on the equidistance theorem. So what this now says is that if I have DE congruent to EF, then HE is a perpendicular bisector of DF. But that's not what it's asking. What it is asking is for you to prove the contrapositive, which we did indeed do. So we can now say that if HE is a perpendicular bisector of DF, then DE congruent to EH. Since DE is not congruent.